Hey there, and welcome. Have you ever just looked around at, well, everything, and wondered how it all holds together? From the phone in your hand to the air you're breathing? It all boils down to how atoms interact with each other. So today, we're going to dive into the amazing world of chemical bonds, the invisible glue that builds our entire universe. So, right off the bat, here's the big question. Why don't atoms just fly solo? Why are they always teaming up to make everything we see? I mean, think about it. We only have about 100 or so types of atoms, but they combine to make millions and millions of different things. What's driving them to connect? The answer in a single word is stability. You see, most atoms, all by themselves, are kind of unstable. Think of a chair with one wobbly leg. It's just not secure. They're constantly on a mission, a quest to find a more stable, low-energy state. And the main way they achieve that is by forming bonds with other atoms. To really get this, let's look at a tale of two atoms. Over here, you've got sodium. See that one lonely electron in its outermost shell? That makes it super reactive, ready to make a deal with anyone. But then you have neon, one of the noble gases. Its outer shell is completely full. Neon is basically the cool kid of the periodic table. It's stable, it's unreactive, it's just content. And pretty much every other atom wants to be just like it.
Now, this whole drive to get a full outer shell has a name, and it's a big one, the octet rule. You can think of it as the #1 rule of chemistry club. The goal for most atoms is to get 8 electrons in octet in that outer shell, which we call the valence shell. If they can get those 8 electrons, they've basically reached chemical enlightenment.
So, okay, how do they actually do it? How do they get that perfect set of 8? Well, it turns out they've got 3 main plays in their playbook. They can give an electron away, they can take one from somebody else, or they can agree to share. And these 3 basic strategies, they give us our 3 main types of chemical bonds. Let's kick things off with the most black and white deal of them all, the give and take. This brings us into the world of ionic bonds, which is basically a simple transaction between one atom that wants to give and another that wants to take. So an ionic bond is what happens when one or more electrons are completely transferred, not shared, but fully handed over from one atom to another. This usually goes down between a metal, which is eager to offload an electron, and a nonmetal, which is desperately looking to gain one. And this transfer, it turns them into charged particles we call ions. Let's watch this play out with probably the most famous chemical couple out there, table salt. So, sodium walks in with one extra electron it desperately wants to get rid of. Chlorine is on the other side of the room, just one electron short of a perfect octet. You can see where this is going, right? Sodium gives its electron to chlorine. Now sodium is a positive ion and chlorine is a negative ion. And what do opposites do? They attract. That powerful magnetic-like pull is the ionic bond that holds salt together. So this transfer creates our ions. The atom that loses an electron, like sodium, becomes a positively charged cation. A fun little way to remember this is that it's positive, like a cat. Get it? And the atom that gains the electron becomes a negatively charged anion. It's that intense positive-negative attraction that creates those strong crystal structures you see in things like salt. Okay, but what happens when you have 2 atoms that both want to gain electrons? Neither of them is willing to just give one up. Well, that situation calls for a totally different strategy. It calls for the Great Compromise. And that compromise is called a covalent bond. Here, instead of a full transfer, the atoms agree to share electrons. This is what usually happens when 2 nonmetals get together. By sharing a pair of electrons, both atoms get to count those electrons as part of their own stable octet. It's a total win-win. Both atoms get what they want, and they end up linked together. This brings up a really interesting point, though. In any kind of partnership, is the sharing always perfectly 50-50? Not really, and it's the exact same for atoms. And the best way to think about this is like an electron tug-of-war. See, some atoms just have a stronger natural pull on electrons than others. It's a property we call electronegativity. Now, if 2 identical atoms are in the tug-of-war, their pull is equal, right? They share the electrons perfectly, creating what we call a non-polar bond. But if one atom is a much stronger puller, it's going to hog the electrons, pulling them closer. This creates a polar bond, with a slightly negative charge on the greedy atom side and a slightly positive charge on the other. And you know what? Atoms don't have to stop at sharing just one pair of electrons. To reach that magic number of 8, they can get pretty creative. They can share one pair for a single bond, like in hydrogen. Or they can share 2 pairs to make a double bond, which is what oxygen does. They can even share 3 pairs, forming an incredibly strong triple bond, like a nitrogen. And as you can imagine, the more pairs they share, the stronger that connection is.
All right, so we've covered giving, taking, and sharing between two atoms. But there's one more type of bonding out there. It's a really unique situation that happens when you get a whole bunch of metal atoms all crowded together. This is called a metallic bond. So what happens here is that in a chunk of metal, all the atoms give up their outer electrons, but they don't give them to any one specific atom. Instead, all those electrons form this big, mobile sea of electrons that just flows around all the positive metal ions. It's not a one-on-one deal. It's more like a giant community pool of electrons that everyone shares. And this electron sea idea, it's not just a cool concept. It perfectly explains why metals behave the way they do. I mean, why are they such great conductors of electricity? It's because those electrons are free to move and carry a current right through the material. And why can you bend a piece of metal without it snapping? Because the atoms can slide past each other in that electron sea without actually breaking the bond. Pretty neat, huh? Okay, so we've just covered the 3 main ways atoms make deals with each other. Now for the really cool part. Let's connect these tiny microscopic bonds to the big macroscopic world that we actually live in and see every day. This table just lays it all out so perfectly. That strong but rigid attraction in ionic bonds is why salt forms those little brittle crystals. The super strong, locked-in network of covalent bonds in diamond is what makes it one of the hardest things on the planet. And that sea of electrons in metallic bonds is exactly why a copper wire can carry electricity and be bent into shape. So here's the bottom line, the big takeaway from all of this. The tiny invisible deal that atoms make with each other, whether they give, take, or share electrons, determines everything about this stuff in our world. How something looks, how it feels, how it behaves, it all comes back to the bonds holding it together. And this leads to one of the most mind-blowing ideas in all of science. Just like this quote says, when atoms bond, they create something entirely new. Just think about our salt example again. You take a dangerously reactive metal, sodium, and a toxic gas, chlorine, you bond them together and you get delicious, harmless table salt. That's not just a combination, that's a total transformation. So there you have it, giving, taking, sharing in pairs, or sharing in a huge community pool. These 3 simple atomic deals are literally the architects of our universe. They build everything from the water you drink to the DNA inside you. So the next time you look at anything at all, just take a second to think about the invisible forces holding it all together. And maybe ask yourself, with all the deals atoms can make, what amazing things haven't